Hello everybody. So we got that quiz coming up Tuesday. It's going to cover day 3 and day 4. So this is your video of me doing all your homework from day 3 and day 4. Let's start with number 1. Excuse me, looking at number 1, I guess let's do everything we can do right away. So we know that we've got no horizontal asymptote. We can see that we're going to have a slant asymptote instead. So horizontal asymptote, none. Vertical asymptote, that is still just the 0 of the denominator, which is 3. So x equals 3 will be our vertical asymptote. X-intercepts. Those are going to occur at the zeros of the numerator. So if I factor that, it'll be x times x minus 1 if you factor out the x. So you see that we're going to get a 0 at 0, and we're going to get another 0 at 1. So those will be our two intercepts. They'll be right next to each other, which is fine. For the y-intercept, well, our x-intercept was already the origin. So when the x-intercept is the origin, your y-intercept is going to be the origin too. I think that about does it for stuff that we can do right now. So that means we now want to do polynomial long division. For that, I'm actually not sure if it matters, but I'm going to go ahead and write this in descending order. So I'm going to go negative x plus 3. I kind of think it doesn't necessarily matter if we do that or not, but I'm going to do it anyway. So we'll go x squared minus x, technically plus 0, but I don't really need that either. So for the first time ever, we've got a negative here, which is going to give us a negative in our quotient, which is going to give us a slant asymptote that has a negative slope for the first time ever. So hopefully you guys caught that. But when we divide, we're going to get negative x. So when we multiply through, we get positive x squared minus 3x. And then we're subtracting. So when I subtract those, they cancel. Remember here you're going to have negative x minus negative, so that becomes negative x plus 3x. That's giving me a 2x. Then sure, I guess I dropped the 0. So negative x goes into 2x negative 2 times. So that gives me negative positive positive 2x minus 6. Subtract, cancel, get 6. So there's 6 as our remainder. So we know that we can rewrite this function as negative x minus 2 plus an extra 6 over 3 minus x. Just leave it like that, I guess. 3 minus x is fine. So I guess the good news is, does this function cross the slant asymptote? Well, no, because we can see that in our remainder expression, the numerator is 6. So if we tried to set this equal to 0 and then cross multiplied, the 3 minus x would cancel. We would just get 6 equals 0, which is just one of those false nonsense statements indicating that the equation had no solution. So there's no crossing of the slant asymptote. So this shouldn't be bad. We'll plot our point at negative 2. And this time, since our slope is negative 1, we're going to go down 1, right 1, down 1, down 1, down 1. So there's the line indicating our slant asymptote, so we can sketch that in. I'm not super paying attention, but you just go diagonally through all the corners of the squares of the grid. We had a vertical asymptote at 3. And then we had x-intercept and y-intercept that were both the origin. We had an x-intercept at 1, 0, so here. Okay, that seems to imply that this branch for sure is going to come just through there. It's going to sneak under the x-axis and then sort of come immediately back up and go up. Again, 999 times out of 1,000, the other branch is just going to be down here. With a simple sort of quadratic over linear, I think we can probably rest assured that that's true. If we had a cubic over a quadratic, then maybe we would be above the slant asymptote and then the next branch would also be above. But I'm relatively certain we're going to be down here. That said, I'm still going to run a test point. So let's test 6. Who cares? If our slant asymptote has an equation of y equals negative x minus 2, then plugging in 6 tells us that sort of the cutoff point on our asymptote is at negative 8. And again, if you've drawn this neatly, you can see that that's negative 8. So I'll plug in 6, and if I get a value that's even less than negative 8, then I know I'm below. I'll plug in 6. If I get a value that's greater than negative 8, then I know that I'm above. So let's just do that math. And again, our factored form is probably the easiest place to do it usually, but this is not a very difficult version of the function to evaluate, so I'll just do it. We're going to plug in 6, so we get 36 minus 6, giving us 30 in our numerator. Then we go 3 minus 6, that's negative 3. So we actually see a nice easy to evaluate one. We're getting negative 10. Negative 10 is decidedly less than negative 8, so we've got a point here. And then we can just kind of rough in the rest. So here I go. Not the smoothest thing I've ever graphed, but it's okay. But that's it. So are we done here? Be sure to indicate any asymptotes. Done. Intercepts. Done. Discontinuities. The only one we have is the asymptote. We will see some examples of graphs today on this homework that have asymptotes and holes, but we'll cross that bridge when we come to it. It says also find the coordinates of any points where the graphs cross their asymptotes. Yeah, so we did that math. We didn't do the math, we just talked about it. We said that because this numerator was constant, there's no way it's ever going to equal 0, there's no way it's ever going to cross, so that's it. Alright, I'm debating whether we want to do like domain and range and stuff, but increasing, decreasing, that's really the purview of day 4, so I'm just going to save it for day 4. If you wanted to, then you guys know my advice is just take this function, plug it into Desmos, because once you're in Desmos, you could find the coordinates of these local mins and local maxes. And once you have those coordinates, you can do the domain, you can do the range, you can do the increasing, the decreasing, you can do all that. So if you want to take these problems as extra practice problems toward finding those properties, be my guest, but I'm not gonna, because I think I'm done. So moving on. Am I done? I'm done. Alright, so we're doing this one now. So I guess I better, excuse me, I need to get a drink. I'm like choking on something. Hold on. Alright, so let's factor. So in the numerator we got to multiply the 2 by the negative 3. That gives us negative 6. So we're hunting for factors of negative 6 that give us sum of positive 1. So 1 and negative 6 won't do it. 2 and negative 3 doesn't do it either, but negative 2 and positive 3 does do it. So that means in the numerator we'll get a 2x, we'll get an x. If I want a factor of 2 or negative 2, I'm just going to put a 1 here. Then my outer product will give me a negative 2x. My inner product wants to be the 3, so I'll put a 3 here. And then the 3 times x will give me what I want. That should be it. That should be my factored form. Downstairs I can factor out a 3. So I factor out a 3 and I get an x plus 2. Nothing cancels, so there's still no holes. So for holes I'll say none. For vertical asymptote, our denominator does have a 0, it's negative 2. And you're supposed to give this as an equation, so I almost only wrote negative 2, but you're supposed to say x equals negative 2, so make sure you remember to do that. I'll say horizontal asymptote again, just as a reminder that we don't have one. Slant asymptote, we have one, but we got to do long division to find it, so I'll do that in a second. X and y intercepts. So for the x-intercepts, it'll be the zeros of the numerator. So positive 1 and negative 3/2. And for the y-intercept, we're going to just plug in 0. Plugging in 0 is going to give us negative 3/6, so negative 1/2. So we've got a lot now. Let's go ahead and plot everything we've got. We know that at negative 2 is our vertical asymptote. We know that We have a y-intercept at -1/2. We have an x-intercept at -3/2. It's right there. We have another one at 1. So we got a big bunch of points right there. That's all we know. So let's do our long division now. So this one looks like a pain in the butt, which, you know, I guess we're used to that from the day 1 homework. So how many times does this go into this? It'll go in 2/3 of an x times. So distribute that through, and you get 2x squared. And then you get what? 4x. And you're subtracting. So it's not that ugly, actually, once you get past the 2/3. These cancel, you're subtracting, so you get -3x. Yep, -3. So to keep going with your division, you get -1, giving you -3x minus 6. So when you subtract, these will cancel. These you're adding, so you get +3 as your remainder. And that's not bad at all. So our quotient is the 2/3 x minus 1. Our remainder is the 3 over 3x plus 6. But technically, yeah, if we can factor the 3 out of the denominator and cancel it, we should. So as much as it's maybe a little bit annoying, perhaps our final answer should really be 2/3 x minus 1. Plus just 1 over x plus 2. But either way, now we can graph our slant asymptote, which is at y equals 2/3 x minus 1. That reminds me, I never actually wrote the slant asymptote down over here. I never even made a space for it, so we'll put it at the top. What's our slant asymptote? Remember, you really are supposed to be writing out the whole equation, so don't forget the y equals, and then the -x minus 2. And that's fine. You could leave it in that form. You could factor out the negative if you wanted to, but you could leave it in this form. So back here, I'm going to go down 1 unit. That's going to get messy. All right, so we'll do it in purple. So we're going to be right here, right where that point is. Then it's 2/3, so we're going to rise 2 and run 3. So I'd be here. Rise 2 and run 3. I'm here. Let's rise down 2 and left 3. Do a couple points that way. That's tough. Alright, it seems to me that all 3 of those points are above the asymptote, right? Sure, seems right to me. So let's go ahead and say that our graph just comes down, 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 hits all 3 of them points, turns, and goes back up, up, up. That's got to be true, because again, looking at our remainder, it'll never equal 0 because the numerator is constant. So we don't cross the slant asymptote, that's for sure. Again, I most likely don't really need to run a test point. I'm pretty confident that our graph's going to fit in here. But I'll run a test point anyway. And I guess that test point will be -3. So if I plug in -3, what do I get? -2 take away 1 is -3? Yeah, I mean, we can see that. We can see that -3 has a y value of -3. So evaluating the function at -3, I get -6 plus 3 is -3. -3 minus 1 is -4. Then I get a 3 times -3 plus 2 is -1. So the 3's cancel. 2 of the negatives cancel. You end up with -4. So -4 is right where we figured it would be, below the asymptote, indicating that the other branch of our graph is entirely below. That's a pretty sloppy looking graph, but I will accept it for now. Any questions? I can't believe I just did that. I held that pause a little extra long. Old habits are hard to break, I guess. You guys aren't there. You can't actually respond to me. So if you have questions, put them in the comments. You guys haven't been using the comments, which is actually a little bit rude. I mean, don't you think you should say, like, hey, Mr. F, that was really nice of you to make this. Thanks a lot. You know, maybe not. Whatever. So anyway, here's 3. More of the same, it looks like. I went over this one in class, maybe for both periods. So maybe you guys are about to hit the fast forward button, I'm not sure. But our numerator is not factorable, and given that there were a couple other typos here and there, you might be thinking that's just a typo and that I meant for this to be factorable, but I didn't. If you look at the quadratic formula, there's this piece in it, right? That's called the discriminant, and you can use the discriminant to check and see if a quadratic has any real roots or zeros or x-intercepts. And so, the whole quadratic formula is negative b plus or minus blah, 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 all over 2a. But I'm kind of just interested in the discriminant here. Let's check and see, because if this thing has real zeros, then they will become our x-intercepts. But I'm saying it doesn't, because if you plug in 5, you get 5 squared minus 4 times 1 times 8. And you're doing 25 minus 32, and you're getting a negative answer for sure, negative 7. So that is telling you that when you use the quadratic formula to try to find your zeros, you're going to be getting the square root of a negative, which is going to be imaginary. And imaginary plus a real part is called a complex number. And complex numbers aren't actually on the x-axis in the real coordinate plane. So this graph just simply must not cross the x-intercept. So when we say x-intercepts, you're going to say none. And that's fine. We don't need x-intercepts. We could still sketch our graph. So what else do we know? We do have a vertical asymptote, like always. It's going to be at x equals negative 3. We don't have a horizontal asymptote. Oops. None. Slant asymptote. Are we going to have one? Well, our degree is definitely greater by 1. This thing's not factorable, so it's not like the x plus 3 can cancel out. Sure looks like we're going to have a slant asymptote. So let's find it. So x plus 3 divides in, it's x squared plus 5x plus 8. X squared plus 3x. Cancel that, 2x, drop the 8. Do it again, plus 2. 2x plus 6. Cancels. 2. I'm going really fast through this because I feel like by now you guys are pretty straight on polynomial long division. If you're not, then you have to see me Monday, right? You've got some time on Monday to get some last minute help. So this function we know can be rewritten as the x plus 2 plus a 2 over x plus 3. So we've got that slant asymptote now. What else have we usually been doing? The y-intercept. So the y-intercept again comes from plugging in 0. If you plug in 0, you get 8. If you plug in 0, you get 3. So we know that it's at 8/3. And as far as whether or not the graph crosses the slant asymptote, again, we still know that it doesn't, because our remainder is another constant. It'll never equal 0. We're only going to cross when if that numerator was x plus something, x minus something, it's got to be at least linear for it to have any zeros. And it's constant, so there'll be no zeros. So let's graph. We can go up to, and our slope is 1. So graphing the slant asymptote should be a piece of cake. Vertical asymptote's a piece of cake. It's over here at negative 3. And again, we don't have any x-intercepts, but we did say we had a y-intercept at 8/3, which is 2 2/3. So 2 2/3 puts you right about here. And again, that 1 point is really all I need to just very roughly sketch in a graph that is probably going to dip down below that point and then come back up through it. I believe we're going to get probably a local minimum somewhere over here at around -1. Check the other side again. Let's just go ahead and test against the -6 like we usually do. -6 you can see has a value at -4. So as we run our test, we're checking to see if we're greater than or less than that value. we don't have a factored form to plug into, so we'll have to plug into just this original form. So negative 6 is going to give us 36 minus 30 plus 8 all over negative 3. So that's what? 6 plus 8 is 14 over negative 3. So that's 4 and 2/3. So that's a little lower because we're down to negative 4 and then an extra 2/3. So that's giving me a point right where I figured it would be. So we're going to be asymptotic to this, coming up, 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 and eventually a local max. And then we turn and go back down. Up, I don't like that. See that bit at the end where the graph kind of flared back in? You guys do that a bunch, and I don't want you to, because that shows the graph failing the vertical line test, doesn't it? Like, we got a point of intersection there, another point there. We really do need to be kind of careful with how we graph. I'm going to go ahead and redraw the whole thing, just as sort of a motivator for you guys to do that too. So up I go, down I come, but continue to get closer and closer and closer to the asymptote. There. That's not perfect. I don't like that little weird bump right there, but it's fine. It's good enough. I'm moving on. Yeah, we're done. Moving on. All right. How about this one? We're going to go ahead and factor first. So 3 times 24 is 72. It's negative 72. And we're looking for factors that add up to 14. So 1 and negative 72, not going to do it. 2 and negative 36, not going to do it. 3 and negative 24, not going to do it. 4, there is a factor of 4. So 4 and 18. Not going to do it, because this gives me negative 14. I want a positive 14. So it's going to be negative 4 and 18. So we now have the target values that we want as we factor. So that should make factoring a breeze. We just know that we need a factor with a 3x and a factor with an x. We can see that to get 18, we can just do 3 times 6. And we want that to be the positive product. So to get the negative 4, we'll put a negative 4 here. That'll get multiplied by x, and we are done. We're factored. So negative 4. Okay, good. And the denominator, again, you could factor out a 4. So 4 and x plus 6. So this was the first question that caught a lot of people sort of off guard, but the x plus 6 cancels, right? So when that cancels, that means your entire expression really just boils down to this linear factor divided by 4. And if you're dividing by 4, you could just divide both terms by 4 and write this as a linear equation, like 3/4 x minus 1. That's just a line, literally just a line. But the fact that this guy canceled out means this is a line that has a hole in it when x equals negative 6. So you're supposed to do that thing where you give me the equation, but you also write down that domain restriction. You say, hey, it's basically just a line, but it's going to have a hole in it when x is negative 6. But that's it. So if we went to graph this now, if we were answering all the same questions, we'd say, I don't even remember how I did this, but let's go vertical asymptote, horizontal asymptote, slant asymptote, x and y intercepts. Is that all we've been doing over and over again? I think it is. All right, so for the vertical asymptote, there isn't one because our denominator canceled out. There's nothing left in the denominator to give us 0, to give us division by 0, to make us undefined to be a vertical asymptote. So there is none. But this is a strange case. There's no horizontal asymptote either, even though my degree is greater than the denominator by 1. Well, my entire denominator canceled out. So I'm not even a rational function anymore, really. I'm not going to have a vertical asymptote. I'm just going to be a line. So that's none. And again, none. There's no slant asymptote either. We're just a line that has a hole in it. So what's our x-intercept? Well, I guess it's 4/3, right? That doesn't feel right. Wouldn't we still set this equal to 0? 4/3, 9/16 minus 1. It doesn't feel right. Yeah, it does. I'm sorry. My eyes are playing tricks on me. Yeah, 4/3. 4/3 would give 1, 1 minus 1 is 0. Alright, I'm being stupid. So 4/3 it is. 4/3 comma 0 is our one and only x-intercept. Our y-intercept is the -1 that we can see on the end of our equation. So 0 comma -1. Let's just graph this. Oh, the whole. Right. So you know that the x-coordinate is -6. But I will be asking you for the y-coordinate too. If you try to plug into the original function, then of course you'll get 4 times -6 is -24, plus 24 is 0. You'll have division by 0 and you won't get a value out of it. So that's why you have to evaluate the simplified version, because I can take the 3/4. I can plug the -6 into that and evaluate, and that's going to work out fine. So what is that, by the way? Looks like if I put that over 1, it's a -18 over 4. And I would rewrite the 1 as 4 over 4 to get my common denominator. So that's looking like -22 over 4, aka -11 over 2, aka -5.5. But I don't like the 5.5, I'm sticking with the 11 over 2. But we could plot this now. We could go to the 6, we could go down 1, 2, 3, 4, 5 and a half. Put a hole there. We could go to our y-intercept at -1, put a dot there. We could use our slope, which is 3/4, to go left 3, down 4. Rise over run. That's got to be backwards. Glad I did this. I'm not going to hit the hole if I did that. It's not left 3, down 4. It's rise over run. So we're rising 3. So we're going left 4 and down 3. I counted from the origin. Oh, gug. It's too late. I'm not doing my best work. Where are we? We should be at -1. Then we can go left 4 and down 3. And then it looks like I'm on target to hit the hole like I'm supposed to. So, okay, that's fine. Our x-intercept is 4/3, so I go 1 and an extra third. Yeah, that looks about on target too. So all of that looks pretty good. So now you can just rough in your line. So there's the hole. Everything else is smooth other than that. Kind of a weird one, but I wanted you guys to definitely see that sometimes with a rational function, your entire denominator can cancel out. And then instead of getting the graphs we're used to seeing, we just get kind of a normal graph, a line that has a hole in it, or a parabola that has a hole in it. Speaking of parabolas with holes in them, I think number 5 is exactly that, or number 6 is. But to do this problem again, you just want to factor. So you factor out an x, and you get x squared minus 7x plus 10 all over x minus 1. So no, this won't have a hole. Well, it might have a hole in it, but it doesn't. Continuing to factor in the numerator, you get x minus 2, and x minus 5. And then the denominator is x and x minus 1. So a lot of information to pull out, starting with vertical, I guess, horizontal, slant, holes, x-intercepts, y-intercepts. Alright, vertical asymptote should be easy by now. It's x equals 0 and also x equals -1. Positive 1. I meant positive 1. Okay, horizontal asymptote is none. Slant asymptote we get by doing the long division. Holes, we don't have any. X-intercept is when we take the zeros of the numerator, so that would be the origin, 0, 0. Also -2, +2, gosh. And 5, 0. And then the y-intercept, well, if you plug in 0, you get in 0. So it's the origin again. So we can plot all that. We're going to have the vertical asymptote at 0. And then also at 1. So I've screwed up, haven't I? My bad. Okay, take all this away. Alright, my eyes glazed right over it. Hopefully you guys are seeing it now. But there's an X right here, and an X right here. So I lied. When I said that there was no hole, that was simply not true. There's going to be a hole whose X coordinate is 0. And to find the Y coordinate, we said we would evaluate the leftovers, essentially, once that factor was canceled. So I could plug right into here. We're going to get -2 times -5 all over -1. So that's 10 divided by -1 for -10. So at 0, -10, right here, we can plot a hole for sure. Alright, feel a lot better about that. At X, so is the origin still an x-intercept for us? Well, no, I screwed up. When I said that we had a 0 at the origin, that was before I recognized that that thing should be canceling out. So there's no vertical asymptote at x equals 0 anymore. And there's not even an x-intercept there anymore either, because we're just undefined there, which means we don't have a y-intercept? Technically, we just don't have anything, because even if we cross the y-axis, it's at a hole. So you couldn't say that our y-intercept is -10, because it's a hole there instead of a dot. So let's keep going. Let's plot what we do have. We do have a vertical asymptote at 1. I think I can stand by that. Okay, and our slant asymptote, we still have to find that by doing the polynomial long division. So I would just take this simpler version and FOIL this back out to get the x squared minus 7x plus 10. And we'll divide the x minus 1 into that, which means we get an x squared minus x, oops, subtract, cancel, adding, so -6x plus 10, so -6 x plus 6, so you're subtracting, so that cancels out, so you get 4. So I guess our final version is x minus 6 plus 4 over x minus 1. And that 4 does tell us that we will not be crossing our slant asymptote because it's a constant, so it'll never be 0, so that's fine. So we go down to -6 and our slope is 1, so you can rough in that line with slope of 1. Okay, good enough. So I don't have a lot of helpful points, but just knowing that that hole is there means that I can just sketch this roughly. We're going to run along this, come up a little higher, turn, come back down, and go out the bottom. The other one we can rest almost certainly sure that the other branch will be up here, but we've got an x-intercept, right? 2 and 5. So we can see for sure that yes, if we pass through 2 and also 5, then we've got our graph. We know that it's up there. We're going to cross, turn, come back up, and go out. But there it is. There's your graph. There's sort of the mini bank of questions. Let's remember to actually do this. Y equals x minus 6. We've got all the other data. Everything's plotted. It's looking good. I'm happy with it. Moving on. So this should be the last, right? Yeah, good. Okay. So doing this last one, this must be the one that's a parabola with a hole in it. But you're going to factor out the x. That's going to leave you with what? X squared minus 7x plus 6, which we can see factors down to an x minus 1 and an x minus a 6. Then, downstairs you see an x minus 1. So what happens when that cancels? A lot of stuff happens. That means suddenly we don't have a vertical asymptote there anymore. We just have a hole instead. And it also means that the graph that we're going to graph is just the other two factors, which would, if you redistribute it, it's just x squared minus 6x, which is going to be a parabola. We know it's got its points of intersection at 0 and 6, so we can plot a point at 0, plot a point at 6. We also know it has leading coefficient that is positive, so it's going to open up. The good news is we can probably tell that 3 represents our axis of symmetry. So we can just plug in 3 to kind of quickly find the minimum value of our parabola and get a good looking sketch going. So that's what I'm going to do. Plugging in 3 gives 9 minus 18 for negative 9. So we know at 3 the graph equals negative 9, and there you've got a well-shaped parabola. But we should probably show its whole, which is at 1, and plugging in 1 gives you 1 minus 6, which is negative 5. So that's right there. So there's a hole right there. But now you can just sketch a parabola. A little too pointy. Smooth that bottom out. Looks too much like an absolute value function. This should be like smoother like that. But it's okay. I'll be fine. You gotta be able to do all the properties again like you always do. So vertical asymptote, it's gonna be none. Horizontal, none. Slant, none. You could do the x-intercepts, y-intercepts, and the whole. So the x-intercepts are 0 and 6. The y-intercept is still at 0, 0. And what? We've got a hole. We know its coordinates. 1, negative 5. I don't think there's a ton more that I would do with this. I think it's fine to be done there. You gathered all the important properties. You sketched the thing. So yeah, I think we're fine. I'm going to save this. It's at 37 minutes already. We can do the next day as its own video. I'll see you guys in class Monday. Bye.